Okay, sorry about that. We had some technical difficulties. All right, so we're moving from searching algorithms to sorting now. So up until this point, we have assumed that either the data that we're working with is unsorted and that's fine, or someone else sorted it for us. But now we're going to look at what it takes to actually rearrange data into a sorted fashion. Now, when we talk about sorting, we usually think of smallest value to largest value. But in the realm of research and data mining and data science, sorting can be anything, any sort of um, uh, ranking of characteristics or when the value was last used. There are all sorts of different kinds of sorting methods that can be used to accomplish different goals. For our purposes, we're going to use the traditional definition of sorting, so from smallest value to largest, and we're going to look at different types of methods that can be used to accomplish that. So the first that we're going to look at is called selection sort, which goes through the collection, the array, many times, each time finding the smallest element that is still within the unsorted part of the array. After each pass through the array, the element that is returned is put into a new array, and at the end of all things, you end up with a brand new array where all of the elements are in that sorted order. Unfortunately, this tends to be a very slow process and rather resource intensive because it requires space for two distinct arrays. So if your array is rather large, then you're just doubling the storage that you must have in order to make this algorithm happen. So a little visualization for you here. This is the high-level description of the sort algorithm. So remember, red means that we're going to define a more complex chunk of the algorithm later. So basically this means the selection sort boils down to a loop that evaluates if there are still elements available in the first unsorted array, and if so, find the smallest element that is left and move it to the next spot in the new array. Conceptually, very, very simple. But unfortunately, each of these chunks, elements available, next find, next smallest, move next smallest, can be a little complex. They have many moving parts, and so in and of themselves can be a little tricky. It also, again, requires you to take many passes through the array because you have to deal with each item individually for every iteration. So you can't just assume that the first item that you come to is going to be the smallest. You have to go through all of the elements every time until you have processed all of them, until they've all been copied to the new array. And again, just to remind you, it takes double the storage. So the larger your array is, the more storage you need. However, we can make some small changes to this initial framework that will allow us to implement the algorithm in a much more efficient way. So for example, let's say that we have a pointer that tells us the index of the first unsorted element in the array. And let's start with 0 because we want to start with the beginning of the array anyway. So our loop becomes, while the array is not completely sorted, find the smallest unsorted item and swap the values of the first unsorted item with the smallest unsorted item. So we're only ever concerned with smaller and smaller portions of the array itself, and everything to the left of the first unsorted index we assume is already sorted. So we can define here that the array not completely sorted logic block is simply whether the first unsorted index is smaller than the last index in the array. So length minus 1. It still requires many passes through the array, but the benefit here is that we're only ever working with the original array itself, and we're not actually duplicating another array into memory. So the array index pointer here is the line of division between the elements that have been sorted and the elements that have not. Everything to the left of the first unsorted index is sorted. That index and everything to the right remains unsorted. So as soon as first unsorted equals the last element array, or array element index, you know that everything has been sorted and we can end the loop. So again, the next smallest item only is found among the unsorted values. Everything to the left remains the same. And when a value is found, you place it in the first unsorted slot. So the pointer, first unsorted, becomes the next sorted element. And then we move the index forward. So this first module here, array not completely sorted, relatively simple, just making sure that the pointer is smaller than the length of the array. Our second module here, finding the smallest unsorted item, deals with comparisons of additional pointers, so it gets a little hairier here. The index of the smallest value is the one that we're looking for. So the index of smallest can move around, so depending on where the next smallest value is in the rest of your array. So starting with the first unsorted value, because again, we don't care about anything that comes before it, that's already been sorted, we then compare after the first unsorted value, we look at the remaining items and find the smallest one that is still left. So while index is less than or equal to length minus 1, so less is still within the bounds of the array itself. If the data at that current point is less than the data of the current value of index smallest, then we know we found the next smallest value. So change the index to point to that new, the index the smallest to point to that new index, and then update the value, the moving value of index, to the next item in the array. So you might have to sit down and actually just ponder this logic a little bit, but basically what's happening is we're keeping a running tally of what array element has the smallest value by keeping track of an index that points to that smallest value. So you might need to just sit and stare at this for a little while and convince yourself that you understand what's going on here. The third module that we have here deals with swapping. So assuming that we've gone through the rest of the array, we now know what the index of the smallest value is. We now need to swap the first unsorted, the value of first unsorted, with the value of index of smallest. So what happens here, and this is a common general purpose little mini algorithm, when you want to swap values, you must have a third temporary storage location to hold one of the values before they can be actually swapped. You can't just set data first unsorted equals data index of smallest and vice versa. Otherwise, you're going to overwrite one of them. So we have a temp item that holds the value that is currently in data first unsorted. We now have a copy of that data, so we can set the existing value to whatever's in data index of smallest, and we update the new value of data index of smallest to the value from the temp item, which was the original value of data first unsorted. So again, you might have to just sit here and kind of ponder this a little bit and convince yourself that you understand what's going on. I understand this can be, kind of hard to wrap your head around. So if you need to, pull me aside and ask for more clarification, I would be happy to do that. In practice, here is a little animation that's going to show you what's going on, and hopefully that will help clear things up. So in this animation, sorted is the division point. So first unsorted is the unsorted little label there. So everything to the left of the unsorted item is obviously sorted, and everything to the right, we move through subsequent iterations, find the next smallest value, which is labeled by the little swooping line thing, and the label min, and then min and the first unsorted get swapped, and we move on to the next iteration. And you can see every iteration through the loop, the sorted portion of the array grows and the unsorted portion shrinks. So if you need to sit here again and just sort of watch it a couple times and convince yourself that you know what's going on, I totally understand. Moving on to the next sorting algorithm, we've got bubble sort. Bubble sort is a unique kind of algorithm that sorts as you go through multiple iterations of the array. I find this one to be a little more intuitive. Unfortunately, the performance is not that great, but at least conceptually it's a little simpler. So going through multiple iterations of the array, bubble sort simply compares sequential pairs of values, and if A, the first element in the pair, is greater in value than B, then you simply swap. And you keep going through the array as many times as you need to until you can get through the whole array without performing any swaps. So we're not going to talk about the actual algorithm for this, but I will show you the animation. And you can see here the subsequent pairs going through the array. 6 is greater than 1, so they swap. 6 is greater than 3, so they swap. And we now have the largest value in the array has bubbled its way up, so to speak, to the last value in the array. In this particular pass, we see 5 bubbling its way up. You get to the last pair comparison, and there's no swap that needs to be made there. And now 4 is bubbling its way up, and then 3 and 2 and 1. So you can see it is a little slower, but at least it's easier to wrap your head around. It's a little more straightforward. And 2 swaps with 3. And now we make our way through the entire array, and there are no swaps, and the sorting is complete. Okay, so now would be a good time to pause the video and complete question 3 of the partner activity, and I will wait until you get back. Okay, so we're going to complete the last portion of our lecture for today. We're going to talk about insertion sort, which deals with the concept that if there's only one item in an array, that's our foundational assumption here, if there's one item in an array, then it is sorted by default. If you have 2 items in an array and they are not in order, they can be swapped, and now the 2 items are sorted. So building from those 2 assumptions, you can now say a third item. So you have 1 item already, now you have 2, now you have 3. If a third item is introduced, it can be placed strategically relative to the 2 previously sorted items. So if you know A is greater than B, B comes first, so it's B and then A, and then you introduce C, you already know the relationships of A and B, and so you can infer, you can strategically decide where to place C. So the algorithm for this guy, a little more condensed than the others. So we're going to deal with whatever current value. We're going to start with 1 because, again, if you only have one element in the array, then it's sorted by default. So we're going to assume that the element in array index 0 is already sorted. So starting with 1, we can compare 0 and 1. So the index that we're looking at is current, which is 1. Place found is not true. So if the data in index, which is 1, is less than the data in index minus 1, which is 0, then we swap them. Okay? And move on to index 0. Now, why is it index 0? This is a little not as intuitive here, but index being 0 is actually a condition that will terminate the loop. So setting index equal to 0, it's now the beginning of the array. We can't move forward. So the loop terminates, and current equals current plus 1. So current is now 2. So we move back up to the first loop. Index is now 2. Place found is false. So moving through the second loop, whatever data in index 2, we compare it against the data in index 1. If it is less than, we swap them. And then we move backward through the array. So 2 minus 1 is 1. So we now compare against index 1. The data in index 1, whatever that value is, compared to the data in index 0. And on and on we go. So as we move forward in the array, we move subsequently backward, and form these additional pairwise comparisons. So the logic for this algorithm is a little more elegant, meaning that it achieves its goals with minimal brute force, with minimal wasted effort. But an elegant algorithm also tends to hurt your brain a little more. So let's look at the animation for this guy. So again, we're starting with the assumption that the element at place 0 is already sorted. And as we move forward, we then compare against everything that we've seen so far. 5 and 6 don't need to be sorted. And it's like a reverse bubble sort. We just move backward further and further until we find the place where the new element would need to be inserted. So you can see it takes very few iterations, very few comparisons to achieve the sorted final state, even though the algorithm itself is not as terribly user-friendly. All right, so to introduce another concept here, we have this idea of recursion. And recursion is a lot of fun because this will be one of those little buggers that melts your brain day in and day out. Recursive logic calls itself. So you can picture if you opened up a dictionary and looked up recursion, you would see definition of recursion. That is pretty well exactly what recursion is. It allows us to utilize the same functional logic and apply it to a variety of data sets in order to achieve more complex goals than would be necessarily available if we were just writing it out all by hand. But you can see this would very easily get muddled and confusing and wrong, so we need to be incredibly intentional in how we lay out the logic. We need to make sure that at some point the recursive loop is going to stop and give us a result. So, it can be a very powerful tool, but you need to be very intentional about how you use it. There are a couple different what we call sub-program models. So if you have a void sub-program, if you think back to your Java classes or anything like that, a void sub-program means you call a procedure, you call a function, you call a method, and you don't care about what the method returns. Public static void main is one of the primary concepts that just get hammered into the heads of Java students everywhere. Public static void main. Void means it explicitly does not return a value, but a void subprogram could be, it could return a value, we just don't use it. We don't care what it is. So you see the program flow here. If your sorting program is executing, and then it calls a function called swap. Then the execution control goes to the swap procedure. The procedure or method or function executes, does its thing, and returns to the primary sort program. And then execution in the sort program continues, regardless of what actually happens in the swap procedure. We don't care. This is different from a value returning subprogram. This is one where the result actually influences the operation, the execution of the main program that calls it. So if your program is going, and calls subprogram B or function or method B performs some calculation we don't really know and returns the result then gets incorporated into our calculation for X. And then X is used later on in the program for whatever we were doing originally. It is these two concepts, a void returning program versus a value returning program, that form the basis of our understanding of recursion. One common example for recursion is the factorial. So if you've ever seen a factorial calculation in math class, it's typically written as some number and then the exclamation point. So the factorial for, let's say, 5, so that would be 5 exclamation point, is every value from 1 to that number multiplied. So the factorial of 5 would be 1 times 2 times 3 times 4 times 5, or 120. Now this could be written out explicitly. So you could type out for every number that you wanted to support, if you wanted to do 1 to 100, you could write out the factorial of 1 is 1. The factorial of 2 is 1 times 2. The factorial of 3 is 1 times 2 times 3, and so on. You can see how this would be very annoying to maintain. You would have to test and debug, and there are many ways that it could go wrong, and we don't want to have to do that. So instead, we write our own method, our own little subprogram, which can calculate the factorial for any number, n. You simply provide the value of n, and it will return the result. So in that way, it is a value returning subprogram. It calculates some value and then returns it. However, we need to have some sort of control method, some control logic to confirm, to force the factorial to end. It can't just keep going forever. So we have here an example where if n equals 0, that is our end goal. To get down to the value of 0, we return 1. Factorial of 0 is 1. Otherwise, we return the value of n times the factorial of n minus 1. So you can see here, factorial of n calls itself. but with a different parameter. And so by subsequently decrementing the value of n minus 1, n minus 1, n minus 1, eventually we will get down to 0, and that is the end game. We no longer, once n is 0, we no longer call factorial anymore. We return just the explicit value 1. And then the execution will bubble back up. So factorial of 0 returns 1. And so you end up evaluating 1 times factorial of 0, so 1 times 1, and you return that value up to factorial of 2, so that would be 2 times factorial of 1 is 2, and that returns up to the value of factorial 3, so 3 times, and on it goes, up to whatever value you were originally trying to calculate. We can also implement binary search recursively. So you can see here, evaluating, remember we had 2 parameters here, first and last. So first being the first index of the chunk that you want to evaluate, and last being the last index. So we can calculate the middle, compare against the value of middle and whatever search item we're looking for, and if no match is found, call binary search again with updated first and last values. If the item that we're looking for is less than the value in the middle, call binary search again with the original first index, but instead of last, call middle minus 1 as the next last value. If the item is greater than data middle, instead of the original first value, use middle plus 1, and continue to use the original last. So at the end, we are simply returning true or false. So if first is ever greater than last, that is one of our conditions, and we can return false. If the search item is actually found, then we return true, and that ends up being our end game. Until that point, simply call binary search again and again with updated first and last index values. The benefit of recursive algorithms is that they tend to be a little more efficient. And in particular, we have what we call the quick sort, which basically divides and conquers. It splits up an array into smaller and smaller chunks until it only has pairs that can be compared and swapped if necessary, if the first value is greater than a second value. The quicksort algorithm can be a little hairy to wrap your head around, unfortunately. So the split value is basically the point at which we are evaluating our chunks. So everything to the left is one new chunk of a split value. Everything to the right is another chunk, and those chunks themselves will then get split and their halves will be evaluated, and those chunks will be split and their halves will be evaluated, and on, again, until we only have pairs, until we only have 2 elements to evaluate, and their values can be swapped if necessary. So determining the split, looking at the values to the left of the split point and to the right of the split point, assuming that you're down to your pairs. If left is less than right, that should be if left is greater than right, then you swap data left and right. Set your split point to the new value and keep going. This is not my favorite description of this algorithm. I understand if you are confused, that's fine. Again, it's not my favorite, but we do have a nice little animation to show how this works. I do not expect you to be experts in this. I do not expect you to be able to apply this. This is more of a convenience. This is more of a I just want you to be aware of how this works, and at this point, just be aware if somebody says quicksort, it means recursion. So this particular animation only shows one particular pivot, so sorting the algorithm according to a single pivot, but at any given value could be your pivot. So you would have to go through multiple iterations until no swaps have to be made. Okay. So moving on to just general abstraction discussions here. You really don't need to understand the ins and outs of this. The point of abstraction, the point of defining these general purpose solutions, problems, how to address them is really, the goal is to be able to apply these particular these algorithms, the steps that you would utilize, to apply them to whatever sort of problems that you might encounter. And I know that's not terribly helpful, but there are many different problems in the world that you will encounter in real life that can be broken down into the same sort of generic, smaller, simpler problems. And if you can generalize those experiences, if you can apply common solutions to new and varied problems, you're going to be so far ahead. So the concept of abstraction here is to take what we already know and to apply it to new problems without having to worry about the explicit details of what's going on and to worry about explicit details. And you do this all the time without really thinking about it. I think we used the example before of a car and not needing to know explicitly how the car operates, how the spark plugs work, how the gas moves through the engine. You just need to know how to use it. And that's the same kind of thing here. With your file system on your computer, you don't need to know how those files are actually stored on the computer. You don't need to know how the data is processed when you open Microsoft Word. You just need to know that everything is going to be where you want it, when you want it, and you can open it when you want it. So the different types of abstractions that we're going to talk about is first data abstraction, which deals with separating the data storage from its use. So for example, if the bank that you work with stores their data as 2's complement numbers. So their banking system, their accounts software stores the data as 2's complement versus 1's complement, or however they store their data. You don't actually care. You just care that when you open up your statement, when you go to an ATM, when you ask the bank teller how much money is in your account, you just care that that value is correct. So the data abstraction there is completely separate from the functionality of the system. You don't care how the data is stored. You just care that it can be used and the data that it represents is correct. Procedural abstraction, we've seen this throughout this entire lecture so far. The logic of a task is separate from how that logic, how that procedure, how that function is actually applied. So, for example, I could implement a sorting algorithm however I want, and as long as it meets your needs of actually sorting your data according to your definition, whether that's value smallest to largest, or whether that's most recently used to least recently used, you don't care how I actually accomplish that as long as your needs are being met. As long as the data is actually being sorted the way you want, as long as it's meeting the performance requirements that you place upon it, you don't actually care how it's being accomplished as long as it meets your needs. And finally, control abstraction, separating the logic of a control structure such as an if statement or a while statement from how it's used. So control structures like if statements and while statements actually have a lot of logic, a lot of internal code that governs their functionality that we are not familiar with, that we don't know how that's being accomplished under the covers. We just need to know that when we use an if statement or a while statement, it's going to perform the way we expect. Now, just to recap, I know that this could be a bit of a trying lecture, so thanks for sticking with me. We covered today what algorithms are, why they're important. We covered the problem-solving steps and strategies from Tuesday, from the Polya algorithms problem solving. We talked about variables, conditionals, loops, and pseudocode. Today we talked about different kinds of searches and sorts, and the nature of recursion and how abstraction helps us out. Now, before class on Tuesday, I just need to reiterate this. Please submit your virtual lecture partner activity responses before Tuesday. Make sure to finish up the Hour of Code and Code Combat activity, whichever one you choose. And remember, it should be fun. Don't stress about it. Just, whatever your skill or interest level is, I just want you to have fun with this. So don't stress. And for next week, I will not be here. I will be at a conference. So Dr. Rohrbaugh will be teaching chapter 10, but please continue to do the reading and the quiz for that, which will also be due before the start of class on Tuesday. Have a great weekend. I will see you when I get back.